Okay, let's look at question number 6 from the 2019 AP Calculus BC exam. I have not read this question yet. I'm solving it in real time. Hopefully I don't make any mistakes. I've already embarrassed myself a couple of times on the earlier questions. All right, so this is your series question. They always wrap up the BC exam with a series question. Nothing like doing a series problem after 3 hours of testing. So we have a function f. It has derivatives of all orders for all numbers x. A portion of the graph of f is shown above along with a tangent at 0. Select values of f at 0 are given. Oh, those select values of the derivative of f. Okay, so those are the second, third, and fourth derivatives are given in the table above. Write the third degree Taylor polynomial for f about x equals 0. And so we're going to crank this out using the Taylor series generation formula, whatever, I can't talk. That would be the nth derivative at 0 over n factorial times x minus 0 to the n, also known as the Maclaurin series. Okay, so f of 0, I'm looking at the graph, is going through 0, 3. F prime of 0 is going to be the slope of the tangent that they gave you, which looks to be negative 2. And then the second, third, and fourth derivative values. There are stupid intercom. Hang on. Okay, yeah, we have a stupid intercom here that sometimes sounds like a police siren. Go figure. Okay, so my third degree, that will be my f of 0 plus f prime of 0 over 1 factorial times x to the first plus f double prime, which was 3 over 2 factorial x to the 2th, and then plus f triple prime at 0 is negative 23 over 2 over 3 factorial times x to the 3rd, and that would be our third degree Taylor polynomial about 0. And if I need to clean that up, I will. Right, the first three non-zero terms for e to the x, oh, that's nice, e to the x, the first three non-zero terms would be 1 plus x squared over 2 factorial, or just 1 plus x squared. Why did I say x squared over 2, I mean. Okay, write the second degree Taylor polynomial for e to the x times f of x about x equals 0. Ooh, interesting. So e to the x f of x is going to be approximately e to the x, 1 plus x squared over 2, times this function, which was 3 minus 2x plus 3 halves x squared, minus, and now I'm going to clean this up, 23 over 2 over 6. That's going to be 23 over 12 x cubed. And I need, what do I need? The second degree. So I only need to go up to x squared. And so as I start expanding this, 1 times 3 is 3. 1 times 2x is negative 2x. 1 times 3 halves x squared is 3 halves x squared. Now I only need the second degree, so I'm going to stop there. And then I'll do x times 3, and I'm going to go ahead and line up my like terms. So I have 3x, x times negative 2 is negative 2x squared. And again, I don't care to go any further. And then I have x squared over 2 times 3, so I'll be 3x squared over 2. And then we will combine all of this. So that's 3 plus x, and then 3 halves minus 2 is negative 1 half, plus 3 halves, oh gosh, 3 halves minus 4 halves plus 3 halves is 1. That's what I thought. Plus x squared. There's our answer. So e dx f of x, whoops, e to the x, f of x is going to be approximately that. All right. Question C. Let h be that function. Use the Taylor polynomial found in A to find an approximation for h of 1. Okay, so part C, h of x is the integral from 0 to x of f of t dt. So h of 1 is going to be the area from 0 to 1 of f of t dt, which will be approximately the antiderivative from 0 to 1. Use the Taylor polynomial found in part A. So I need to go back up and see my answer to A. Oh, geez, why is it jumping around so much? Stop doing that. Okay, I'm just going to copy and paste it. Oh, wait, I cleaned it up right here. So let me grab that. Can I get it? Heron group. Okay, so there is my polynomial from part A. So let me copy that. Let's paste it. Bring it down. Stop doing that. There we go. All right, so there is what we're going to do, dx. And so we'll find the antiderivative. That's 3x minus x squared plus 1/2 x cubed minus 23 over 24 x to the fourth. We'll evaluate that from 0 to 1, which would be 3 minus 1 plus 1/2 minus 23 over 24 minus, and when you plug in the 0, you get a bunch of zeros, so there is our answer to C. So far, this is a fairly nice series question, I think. Question B, that's a little bit unique. Usually that's not the way we alter series by the expansion method. That doesn't happen very much, but still not terrible. It is known that the Maclaurin series for H converges to H for all real numbers X. It is also known that the individual terms of the series for H of 1 alternate in sign and decrease in value to 0. Decrease in value to 0. Use the alternating series error bound to show that the approximation in part C differs from H of 1 by at most 0.45. Okay, so the approximation in C differs from H1. So your error, because they gave you the conditions in the paragraph, the alternating series error test is your error is always less than your first omitted term. So to find my first omitted term, I actually need to go back and find what would have been my x to the 5th term for h of x. So I'm going to have to go all the way back, and my, geez, this scrolling is going to kill me here. So we were doing a series for f. My next term would be the 4th derivative of f at 0 over 4 factorial times x to the 4th. And the 4th derivative of f is 54. Holy cow. 54 over 4 factorial. 4 times 3 is 12 times 2 is 24. X to the 4th, right? And so my very first omitted term, therefore, the first omitted term in the approximation of h of 1 is from the antiderivative of that, which would be 54x to the 5th over 24 times 5, and 24 times 5 is 120. And then at 1, that would give me 54 over 120, and we're trying to show that that is at most 0.45. Is that indeed less than or equal to 45 over 100? And I think it would be. I feel better doing the arithmetic to get this all the way down, so I can divide that. That's what, 27 over 60, which continues going 9 over 20 is less than, and less than or equal to, oh, there we go, 9 over 20. Okay, so that actually was equal. So 9 over 20 is the same thing as 45 over 100. Therefore, error is less than that. My wording, I'm kind of tired of working these problems. My wording is probably good enough. I don't know if this is how AP readers would be happy with you writing it. You do want to reference the first omitted term because your error is always less than the first omitted term. I guess I'll write that. The max error in a convergent alternating series approximation is less than or equal to the first omitted term which equals 45 over 100 in this case. All right, so there, that's good enough. We are now done. We got exactly the value we needed for the error approximation, and I'm going to quit.